All right, welcome to Unit 2, Exploring Two-Variable Data for AP Statistics. We are in the middle of Topic 2.8, Least Squares Regression. Now, we already watched Part A, and now we're going to move on to Part B. So in Part A, remember we talked about why it's called the least squares regression line and why it really is the best line. And then we also explored how the heck to get the least squares regression line model, like how to build the line y hat equals a plus bx. Now we're going to turn our attention to what do slope and y-intercept mean? Like, I have taught you how to find them. It's actually pretty cool. It's pretty simple. And like I even mentioned, in most cases, I will give you A and B, but being able to interpret what they mean is really important. So this is a big task that I'm telling you right now is going to be on a quiz. It's going to be on a test. It's definitely going to be on the AP test. So we have to make sure we understand to explain what the slope and y-intercept, what they mean in context. So let's first remember what slope and y-intercept mean in algebra. So the slope is rise over run. It tells us how much the y variable increases for each increase of 1 in the x variable. So basically it tells us how much our line goes up and over or down and over. Could also decrease. The y-intercept is where a graph crosses the y-axis. If you recall, this is what happens to y when x equals 0. Y-intercepts look like this, 0, y. So every y-intercept in this world has an x value of 0. So the y-intercept is what y is when x is 0. We just have to become good at applying these two concepts of slope and y-intercept to an actual problem with actual numbers. All right, so let's go over slope one more time, a little slower. All right. The slope tells us how much the response variable y is predicted to change for each increase of 1 in the explanatory variable. The key word there is predicted. Remember, we're never going to say that x will make y change. It's just a prediction. So the slope is nothing more than how that response variable y is predicted to change for each increase of 1 in the explanatory variable. So let's practice this a little bit. Let's just say your slope is 3. Well, the first thing I like to do is make it a fraction because I remember from algebra, slope is y's over x's. So this tells me that for the response variable will increase by 3 units for each increase of 1 in the explanatory variable. All right, even if my slope is a decimal, no big deal. Still make it a fraction by putting it over 1. Y is on top, x is on the bottom. That is how you find slope. So this particular slope tells me that I would predict that the y response variable will go up by 1.5 units as the explanatory variable increases by 1 unit. So the explanatory is always increasing by 1. All right, what if your slope is negative? Well, same thing. Put it over 1. The 1 is always the x. The number is always the y on top. And we would say this time I predict the y value to decrease by 7 units for each increase of 1 in the explanatory. Even if it's a negative decimal, still make it a fraction by putting it over 1. The 1 is always the x, and the slope is the y. So basically, this would tell us that the predicted y variable, the predicted response variable, will decrease, because it's negative, by 0.45 units for each additional 1 in the explanatory variable. Right? So for example, -7 means it's dropping really fast. -0.45 means it's dropping pretty slow. You guys get slope, I hope. All right, now we just have to learn how to put some context to that with an actual problem. But you need to understand that you can always make a number a fraction by putting it over 1, and the 1 is always the explanatory variable's movement. All right, what about the y-intercept? Well, remember, the y-intercept is what we predict the response variable to be when the explanatory variable is 0. So the a value, the y-intercept, is always what we expect the prediction to be for y when x is 0. So for example, if your y-intercept is 450, I would say, well, if my explanatory variable is 0, I would predict a y value of 450 units. If it's 66, I would say, well, if my explanatory variable is 0, I would predict the y to be 66. It can even be negative. If the explanatory variable is 0, I would predict the response variable to be -75 units. Even if it's a decimal, doesn't matter. If the explanatory variable is 0, I would predict the response variable to be 2.56 units. So keep that kind of rhythm going, right? It's what we predict the y variable to be when x is 0. Now, I do want to note that sometimes the y-intercept will not make sense in context due to extrapolation. Like the y-intercept is always what happens when x is 0. Well, if none of your data was around x equaling 0, then it's probably not going to make a whole lot of sense because remember, we talked about linear regression models are only good for where the data came from. So remember, this is completely okay. This doesn't mean that the y-intercept is wrong or bad. It just simply means the context of it might not make a whole lot of sense. All right, let's actually put this new concept to use in our truck problem. So back to trucks. Now remember, I gave you this equation. The equation is y hat equals 38,257 minus 0.1629x. First off, please note that the slope is next to the x. It is the negative 0.1629. All right, what does that slope tell us? Well, here it goes in context. The price of a Ford F-150, sorry, I forgot the zero there. The price of a Ford F-150 truck is predicted to decrease, because it's negative, by about 16 cents for each additional mile that is added onto the truck. So remember, always take your slope and put it as a fraction. The 1 is always the x. The actual slope value is the y. And then don't forget the word predicted because no one's guaranteeing this is going to happen. But this is basically telling us that as we increase 1 mile on a truck, the predicted price of the truck will decrease by about 16 cents. Now notice that I did convert that to a unit by using dollars. So please do not forget units. So for each additional 1 mile, I can even put a 1 in there, but I think it's implied that a mile is 1 mile. But it's pretty easy to interpret this. It's not overly difficult. Just don't overthink it. It's almost like a script. You just got to follow the script, right? It is how much we predict the response to change for each one in the explanatory. All you got to do is fill in the blanks with the context. So for this particular one, I'll say it one more time. We predict the price of a Ford F-150 truck to decrease by about 16 cents for each 1 mile that is added onto that truck. All right, what about the y-intercept? The y-intercept is A, and that is 38257. And this is what we predict a truck with 0 miles to be worth. So the predicted price of a truck with 0 miles on it is $38,257. Notice the units, miles, and a dollar sign. And you could say this backwards if you wanted. You could say $38,257 is the predicted price of a truck with 0 miles on it. I don't really care on the order. Just be careful that it makes sense. And the y-intercept always has an x of 0. Now, I will say that, as I mentioned earlier, this might not make a whole lot of sense. Because if you remember our truck data, none of the data was near 0. I think our lowest was about 8,000 miles and our highest was about 140,000 miles. So making a prediction about 0 miles is extrapolation. It is outside of our data. So I don't know if this is going to hold true or if this is going to make sense, but it doesn't mean it's wrong. It's still the correct value to use. It just might not make sense in context to our problem. All right, I cannot tell you enough that you will be tasked on a test, quiz, homework assignment to explain the meaning of slope and y-intercept. It just takes a lot of practice. And another video that's going to come after this one will be another problem that we could practice this skill on. All right, let's move on to the last topic. How reliable is a linear regression model? All right, before we answer this question, let's first go back to what we've already learned. In earlier topics, we learned about how to check if a linear regression is appropriate. Now remember, there's 2 ways to check for appropriateness. Number 1, you got to make sure your explanatory variable versus your response variable, your scatter plot, it needs to look somewhat linear. I mean, if you see a giant curve in your scatter plot, don't use a line. And the second thing we introduced you to was a residual plot. And we want a residual plot to be completely random, no pattern at all. Remember, that's a good thing. And you can go back in that video and watch that if you need a better explanation for that. But those are the 2 things to check if you're asked about appropriateness. Now, appropriateness is simply making sure that the line is the right model to be using. But now we want to explore reliability. Reliability is basically saying, hey, how good is our line at making predictions? Now that we know our line is the right thing to be using, how good is it at making predictions? And that's what we talk about when it comes to reliability. Now, there are two different values that will explain reliability to us, and we're going to review them now. All right, the first value is called the coefficient of determination, or R squared. Now, I would like to first pause for a second and kind of admire the name of this. Coefficient of determination. I mean, that's probably one of the coolest vocabulary words we're going to learn all year. But literally, all the coefficient of determination is your correlation squared. Just take R and square it. It's not that complicated. So if you know R, square it. Now, when you square it, it's going to become positive. Even if R is negative, it's still going to become positive. Now, what does R squared tell you? Well, it tells you it is the proportion of variation in the response variable that is explained by the variation in the explanatory variable. Now, this is definitely a tough concept to understand, but think of it like this. How related are two variables is what we're exploring in this entire unit. And think of the R squared as a percentage, right? It's a proportion, percentage. And it's basically a percentage that tells you how linked these two variables are. Because if you look back at our truck data, there was a lot of different mileages on trucks. I mean, it was definitely varying, right? There was a lot of variation. Some trucks had a lot of miles, some trucks had a little miles. And there was also a lot of variation in price. Some trucks were cheaper, some trucks were more expensive. They varied, right? And what R squared is telling you is that the variation in prices is actually linked to the variation in mileage. Different mileage, different price. And R squared simply tells you how strong that relationship is. So obviously 100% is like, duh, the Y value is definitely explained by the X value. They are definitely linked. I mean, 100%, come on. Now that's only going to happen if your R value is 1. So even if your R value is strong, like let's just say your R value is 0.9, pretty strong. When you square it, you get 0.81. And what that means is that 81% of the variation in your response variable is actually due to or explained by the variation in your X. And 81% is pretty good. Is it a perfectly strong, grip? No, but 81% is still a pretty good connection. And that's what R squared tells us. So in other words, it's the percent of variation in the Y variable that is explained by the use of the regression line. Because when you use this regression line, all of your predictions are not going to be perfect. Some are going to be a little high, some are going to be a little bit low. And this tells you how close you are together with those variation in Y to X. All right. Now, once again, I'm never going to ask you to find R. I'm always going to give it to you. And if you know R, then you could square it to get R squared. What I actually care most about is that you know how to interpret what the coefficient of determination is. And it's literally just, it's the proportion of variation in the response variable that is explained by the variation in the explanatory variable. So if you need a lot more help with that, then, kind of see me in class and I can help you with that. But it's not too difficult. You just have to make sure you take a moment to kind of process what I just said. Maybe go back and play it again and see if you understand it. Now, let me actually look at a scatter plot here so you can maybe try to understand this, right? So here is a scatter plot of calories in cereal versus the number of carbs in cereal. So we looked at several different cereals and we looked at how many calories were in a serving versus how many carbs were in a serving. And, clearly I see a very linear scatter plot and my linear regression model fits it very, very well. And what I like most is that all of the residuals are very, very small. So obviously these two variables are very, very strongly connected. Now, I don't remember exactly what the coefficient of determination here is, but let's just say it's something like 0.95. Well, that's really strong. That means 95% of the variation in carbs is actually explained by the variation in the number of calories. So that is showing how well calories are connected to carbs for cereal, right? And when you see a very, very strong, nice linear data, you're going to have a very, very strong R squared. All right, here's another one that is actually a little bit weaker. And I did that on purpose so you can understand that. So here we look at the weight of a high school student and their max bench press. And the scatter plot is barely positive, but it does look like if you weigh more, you could bench press more. But what you notice here is it's not as reliable, right? Like there's a little bit more scatter. Now, some points have small residuals, but other points have some large residuals. It's not as tight and compact as the previous graph. So maybe this R squared value is like 75%, right? So 75% of the variation in bench press weights are actually because of the variation in weight. So it's still a connection, still a pretty good connection, but just not as strong as 95% per se. And that is exactly what R squared tells you. All right, the second number that can help us understand how reliable data is, or how reliable a regression model is the standard deviation of the residuals. All right, so first, remember that a single residual is how far off a single point is from what it was predicted to be. So one residual at a time is simply how far off that actual value was from what it was predicted to be. Well, the standard deviation of all the residuals is basically how far off a typical point is, right? So instead of looking at how far off one point is, the standard deviation of the residuals is a way of looking at how far off typical points are. So think of it like an average, right? Like every point is off a little bit, whether above or below. So think of this like an average residual size. And in other words, think of it like this. When you use the linear model to make a prediction, the standard deviation tells you how far off that prediction typically will be. Now, some predictions are better, right? Some residuals are smaller. Some predictions are worse. Some residuals are bigger. So the standard deviation of the residuals is just basically telling you the average size of residual, how far off a typical point is when we use our model. All right. Now the abbreviation for this is S, because it is a standard deviation. But when you're working with two variables, it's not just the standard deviation of the Y. It's not just the standard deviation of the X's. It's the standard deviation of the residuals. Hopefully that makes a lot of sense. Now, as the kind of theme has been going, I'm never going to ask you to calculate this value. I'm going to give you this value. I just want you to know how to interpret it. Now, keep in mind, the residuals are measured in Y, right? Remember, residuals are the actual Y minus the predicted Y. So they're Y variables. So that means the standard deviation of the residuals is also a Y. So keep in mind, the units on S are the same units for Y. Keep that in mind. All right, what I think it's best to do now is we kind of learned a lot. Let's actually apply everything we've learned to a problem that we've already looked at. All right, so here is our truck problem. And remember, this is one of those computer output tables, which is just a nice way that I can give you everything you need. Remember what I explained to you in the previous video. You don't need the column for SE. You don't need the column for T or P. And what you do need are the coefficients. And that's in alphabetical order, your y-intercept first, and then your slope B. And then what you'll see typically in one of these computer output tables, they will give you R squared and they will give you S. So again, you don't have to worry about finding those numbers. I will give them to you. So let's make sure that we know how to interpret them. So I already have the answers laid out here for you, and this is what I expect of you on a test or a quiz. All right, what does R squared tell me? Well, it tells me that 66% of the variation in truck prices, that's Y, are explained by the variation in the number of miles on a truck. So, the number of miles on a truck clearly has something to do with the price, but it's just not a perfect something, right? Like it's a pretty good connection, but it's about 66%. You can look at it that way, right? So you just have to make sure you word it properly. 66% of the variation in truck prices are explained by the variation in the number of miles. So if we go back and look at our data, we see a bunch of different prices and we see a bunch of different miles. Well, 66% of the different prices are actually because of the different miles on the truck. Variation is just a fancy word for different. All right, what about the standard deviation of the residuals? Now I see here it's 5740.13. Now remember, the unit is the same as Y, which is price, dollars. So the standard deviation of the residuals tells us that when we use the line to predict the price of a truck, we're typically off by $5,740.13. Now, let's just review that one more time. Remember, the standard deviation of the residuals is basically telling you how far off a typical prediction is. Now, if I ask you to make an actual prediction, then you could find the actual residual, right? Because you could do the actual price minus the predicted price. But the standard deviation of the residuals is more like a general thing, right? It's basically saying, in general, when we use this line to predict the price of a car, we're going to be off by about $5,700, right? All right, give or take, right? We're going to be off by a little bit. Maybe we're off by more, maybe we're off by less, but that's like an average price that we're going to be off by. Now, why do these two concepts, coefficient of determination and standard deviation of the residuals, talk to us about reliability? Well, because, I mean, if you think about it, if you're going to use a linear model to make a prediction, the standard deviation will tell you how far you're off by. I mean, let's be honest. If my standard deviation here was only $5, oh my gosh, I'm doing a really good job at making predictions. My predictions are only off by $5? Then that's going to show a very reliable line that is going to really help you understand the price of a truck based on its price. Now here I'm off by almost $6,000. So how reliable is this? Well, you know, when you're estimating the price of a car and somebody's off by $6,000, that's kind of a lot, to be honest. And the coefficient of determination tells us how connected these are, right? If the connection is 99%, well, then that's pretty reliable. That means that the mileage of a truck has a lot to do with the price of a truck. Well, here we're only 66% connected. So, I mean, that's not terrible, but it's nothing I'm going to write home to my parents about. It's just kind of average, I guess, right? So if I said to you, is this model reliable? I would say somewhat reliable. You know, and the answer is why? Well, you know, if you think about the price of a truck, there are lots of things that go into it. The type of truck, how many miles are on the truck, how clean the truck is, does it have any dents, does it smell bad, what year it is, how old it is, not just how many miles are on it. So there's lots of things that go into the price of a truck besides just the miles on it. Do the miles have something to do with it? Sure, about 66%, but they don't have everything. So keep in mind that we're separating the two questions. Appropriateness. Is this line appropriate? Absolutely, because we saw in the previous video that the scatter plot looked linear and the residual plot showed no pattern. So that's a different question. But now we're focusing on reliability, which is just making sure that the line we're using is good at making predictions. And for this particular question, it's like it's not great, but it could be better. All right, guys, that's it for this video. There is going to be a third video that just gives one more practice problem. And I don't explain everything. I just give you the problem and give you the answers. So it allows you to kind of have a chance at practicing these skills that we have learned. All right, I know that there's a lot of information in this topic for 2.8, but it just takes a lot of practice. We're going to do a lot of worksheets. We're going to do a lot of examples so that you can get a hang of it. And honestly, the one thing you have to study is the script. Like, you have to know what to say and when to say it when you're asked. So if you study that and practice that, the more you practice it, the better you'll be for a test. All right, guys, see you in the next video.